Today we're going to start force diagrams, or some call them free body diagrams, and they're just drawings of an object and all the forces that are acting on the object. And they can show whether forces are balanced, meaning there is no net force, so there would be no acceleration, or whether forces are unbalanced, so there is a net force which would cause an acceleration. And we're going to stick with Newton's second law here, and one of the most important forces we're going to draw, that you're going to draw for virtually every force diagram, is the force of gravity. And here on Earth, the force of gravity is mass times Earth's acceleration of gravity of 9.8 meters per second squared. And just to send home the point that it's a force, we need to make a distinction between mass and force. Like, my mass is 83 kilograms. And if you remember from chemistry, mass is the amount of stuff an object is made of. So I have 83 kilograms of atoms and protons and neutrons and electrons in me. And it doesn't matter if I were sent to the moon or to outer space or to Jupiter, my mass will always be 83 kilograms because that's the stuff I'm made of. If you want to talk about my weight or the force of gravity on me, that's a different idea. Mass is the amount of stuff. Weight is your stuff in a gravity field. So for me, the force of gravity would be my 83 kilogram mass times the Earth's acceleration of 9.8 meters per second squared, which means my weight is 813 kilogram meter per second squared, but we just call that a Newton, so my weight is 813 newtons. That's the force of gravity on me. My mass is only 83 kilograms, but my weight is 813. So if we were to draw a force diagram for me, the force of gravity for me would be 813 newtons. And that's true for every object. You have to multiply the mass times the acceleration of gravity. So let's go through a couple here. And so you have a worksheet, force diagrams worksheet 2, and I'm going to run through a few of them and leave the rest of them for you to finish. Okay, so here I'm going to draw a force diagram for a motionless cat on a rug. First, we need to talk about the possible forces, and we only have a list of 5 possible forces we're going to use for our diagrams. And the first one is gravity, because you're going to draw a gravity vector for any object. So the kitty certainly has a force of gravity, and what we're going to do is we're going to put the kitty in the middle of the Cartesian axis, and we're going to draw the force of gravity pulling the kitty down. Gravity will always point straight down no matter what. And remember, that's the kitty's weight. So it would be the kitty's mass times 9.8. We have the normal force, and that is the force of a surface pushing up on an object. Most of you are probably sitting down right now, so there's a normal force on you. You have gravity pulling you down, and you have the normal force pushing you up. If all you had was gravity, then you should accelerate. Newton's second law says there's a force acting on you, you should accelerate. But there is an opposite force in this case, a normal force pushing the kitty up. Okay, there's a possibility of having a tensional force, and that means if there's a rope or a wire or something pulling or holding onto an object, but we don't have that for the kitty. We can have a push or a pull, and be from an engine or a person or whatever, pushing or pulling an object, and then the force of friction. The kitty doesn't seem to have friction, it just seems to be sitting on a carpet motionless. And here's the key. If you go back to our graphing, the kitty's velocity is 0 and constant, so the kitty has no acceleration. So for Newton's second law, rearrange for acceleration, the acceleration of the kitty is the kitty's, all the net forces acting on the kitty divided by the kitty's mass. Well, we know that the net forces are 0 because the normal and the gravitational force cancel each other out, so the kitty's acceleration is 0. And we can put little equality marks on those forces to tell us that the normal force and the gravitational force are equal, therefore there's no net force, therefore the kitty's not accelerating. If we move to the second one on your sheet, it's a skater moving at constant speed across frictionless ice. All right, so possible forces. Again, we're going to have gravity. Straight down, always straight down. And since the skater is on a surface, there is going to be a normal force, straight up on the y-axis. Now, we can go through and look at tension, but there's no wire or chain or anything like that on the skater. There's nothing pushing or pulling. That doesn't say the skater's pushing off. It just says the skater is moving at a constant speed. It says it's a frictionless surface. So there's no friction, there's no other vector we can draw other than gravity and the normal. And so for our graphing, the skater is moving to the right here in the picture, so that's a positive constant velocity with no acceleration. And no acceleration means that the net force is zero, the acceleration is zero, and that's because the forces or cancel each other out. There's no net force. Next one on your sheet is a ball rising in a parabolic trajectory. So this is the ball has been thrown up and has left, whoever threw it has left their hand, and it's just simply on its way up. You know, it'll go up and it'll come back down. But we're going to talk about whatever forces are actually acting on this ball. And if we always keep in mind Newton's second law that the acceleration of the ball is equal to the net force over the mass, well, the only thing really acting on this ball right now is gravity. So the net force is going to be the force of gravity, which is going to give us an acceleration of negative 9.8. So I know there's a force of gravity. Every object has a force of gravity straight down. And there is actually no other force involved. There's no normal force because there's no surface. There's no wire or anything like that to have a tensional force. Nothing pushing or pulling it after it's left the person's hand. And we can say the friction in the air is negligible. So the only force operating is that force of gravity, so that ball will accelerate at negative 9.8 meters per second squared. And graphically, that means the ball starts fast in a positive direction and slows and slows and slows to the peak, and then it will speed up and up and up as it comes back down. And that has a slope, and it's a negative 9.8 constant acceleration of gravity. The next one is the same ball, but at the top of its arc. So it's been thrown up, and it reaches the peak of its trajectory, and it starts to come down. Well, we still know that it's gravity is the force acting on it. And since the only force acting on it is gravity, its acceleration is negative 9.8 meters per second squared. So we certainly have gravity, and there's no surface for a normal, there's no tension, there's no push or pull, there's negligible friction. The only force is gravity, and that's why we have an acceleration. And it's exactly the same wherever the ball is in its path. Okay, and now this one isn't on your sheet, but we need to talk about how we deal with if the surface is not flat, is not horizontal. So we're going to draw a force diagram here for this beach ball sitting on a hill. So we have our Cartesian axis. We've got x and y, and we're going to put the ball right in the middle, and there's certainly going to be gravity pulling down on the ball. The ball is sitting on a surface, so there's certainly going to be a normal force. And normally those balance out. And we can think about, oh, wait a minute, the ball is rolling down the hill. If you look at our drawing, the ball shouldn't move. There is no net force. So the ball should just sit there. So there's something wrong with our drawing. We can't draw a force diagram for something sitting on a slope in the same way that we do for anything sitting on flat ground. I know the ball is going to roll down the hill. So there has to be something else we can do. Okay, I know that there's an acceleration because there is a net force. So what we need to do anytime there's a tilted surface, you have to tilt your Cartesian axis to match that tilt. So the x-axis is going to be our surface. Whatever that tilt is, no matter how big or small, you've got to tilt your axes. And then when you draw your forces, gravity is still straight down. It's always straight towards the center of the Earth, even if the surface is tilted. There's still going to be a normal force, and it's still going to be perpendicular to the surface, so it's going to be right on the y-axis. And now you can see that the forces are unbalanced. They go to the right, and that's the unbalanced net force that causes the ball to accelerate. And how we deal with this is, if you'll see, gravity is not on the y or the x-axis. It's in between them. That means gravity in this case is pulling both down and to the right. So we're going to break the force of gravity up into its x and y components, and we're going to label those F of g in the x and F of g in the y. So now you can see that the normal force is balanced by F of g in the y. That's why the ball isn't accelerating up and down. It's accelerating to the right, and what's causing that is the net force of F of g in the x, and that gives us some sort of acceleration that moves the ball down the hill. Okay, do another example here. We have a puppy sitting on the same hill. We got our same axes, but since the surface is tilted, we're going to tilt the axes. The puppy certainly has gravity. There's a surface, so there's going to be a normal force. And this is still unbalanced to the right. So there's something, we know there's gravity pulling the puppy to the right, but there must be something that's preventing the puppy from sliding down the hill, because it says the puppy is just sitting there. Well, we have our list of forces. We have gravity and normal. There's no wire or anything for a tension. There's no push or pull, but there certainly is a frictional force opposing the puppy sliding down the hill. So that would be the other force that's balancing it out so that we have no net force and no acceleration. We're still going to break gravity into its x and y components. And since we know that the puppy is not accelerating up or down, into the hill or off the hill, I know that F of n equals F of g of y. And because the puppy's not accelerating along the x-axis, up the hill or down the hill, I know that the frictional force is equal to the gravity and the x force. We don't even need, and so we have no net force and no acceleration. And we don't even really need to keep that original gravity force on there. This force diagram shows us that all forces are equal, up, down, and left and right. Therefore, we have no net force. Therefore, we have no acceleration, and the puppy is motionless. So here, let me do one here, and then I'll leave the rest to you. You're going to draw a force diagram for a water skier at constant velocity. Well, if you look at it, the water skier is on a little bit of a tilted surface, so we have to tilt the surface. If you don't tilt it, then you won't know what forces are actually pulling the water skier left, right, up, or down. You've got to, since there's a hill, even if it's on water, you have to count for that surface being tilted. Certainly going to be gravity, certainly going to be a normal force. And if you look, there's a tensional force of the boat pulling with the rope, pulling the water skier. All right? And we're going to need to break gravity into its y and x components. So force of gravity in the x and force of gravity in the y. You can say there's a friction, but that's not necessary. We can explain it with just gravity, tension, and the force normal. I know that the water skier is not accelerating up and down into the water or up off the water, so I know the force normal is equal to the force of gravity in the y. And it's not accelerating left and right because it tells me it's at a constant velocity. So I know that F of g in the x is balanced by F of t, the tension from the rope and the boat pulling it. I think I'll leave the sled and the kids for you to do. And I think I'll leave the rest of them for you to do. Remember, you come to one where there's a squirrel sitting on a roof, so the squirrel is motionless, so no acceleration means no net forces, so they all have to balance. And you have to tilt the surface. You have one where there's a snow skier heading downhill and is accelerating, so there is a net force on the snow skier. and the surface has to be tilted. And there's a person hanging from, well, it's one wire, but it's really two wires. So two tensional forces holding this person up, and certainly going to have gravity. So go ahead and give those a shot.